Hello, I'm Scott Crawford, a researcher at the National Energy Technology Laboratory, or NETL, and the principal investigator for a groundbreaking project that has advanced the use of luminescent sensors to detect several key rare earth elements, or REEs, in fossil energy byproducts. I'm pleased to join you to discuss our exciting work, which was published recently in RSC Applied Interfaces. NETL's low-cost fiber optic sensor exploits a process called photoluminescence sensitization to detect REEs, critical materials needed by the United States manufacturers to make high-tech devices, and waste byproducts generated from mining and fossil energy production. Currently, the United States imports the vast majority of the REEs it needs to manufacture electronics and computers, defense systems, solar panels, and much more. Our technology is a critical step forward to help establish a domestic supply chain of REEs and end U.S. reliance on offshore producers. To help meet this challenge, NETL has developed a fluorescence-based sensor that uses materials called metal organic frameworks, or MOFs. MOFs are highly porous crystals that form by reacting metal ions with organic linkers to produce materials with large surface areas. Think of them as microscopic sponges, as you can see in this electron microscope image. In previous research, we found that one particular MOF, BTC1, was highly effective at detecting REEs in waste streams such as acid mine drainage. We improved upon our previous efforts by essentially gluing BTC1 on the tip of an optical fiber, like the one I'm showing here. The MOF-coated tip is then attached to a compact, NETL-built fiber optic spectrometer. When the MOF-coated tip is exposed to REEs, the positively charged REEs are pulled into the negatively charged MOF. Ultraviolet light from the excitation source moves down the optical fiber tip, and the MOF undergoes photoexcitation. Now, some of that excited state energy is transferred from the MOF to the encapsulated REEs, creating unique, element-specific, narrow emission lines that can then be used to detect and distinguish the REEs europium, terbium, samarium, and dysprosium. Using this technology, we can detect the REEs down to part per billion levels, and we've applied this sensor to both spiked acid mine drainage samples as well as a simulated process stream, which indicates that this device can function in relatively realistic environments. After RE exposure, we can remove the tip from solution and dry it, thereby significantly boosting the luminescent signal. Plus, we can recycle the sensing material for at least 10 cycles by exposing the tip sequentially to the RE solution and then dilute hydrochloric acid. In the longer term, we can also envision immobilizing other sensing materials onto our fiber optic system to target other valuable metals or further improve performance. In closing, I want to acknowledge the outstanding contributions of my co-authors at NETL. The efforts of colleagues Ward Burgess, Ki-Jung Kim, John Baltras, and Nathan Daimler were instrumental in advancing a technology that demonstrates promising potential to produce an affordable domestic supply of crucial REEs to protect the energy, economic, and national security of the United States. Thank you.